Hello, my name is Evans Morales, and today I would like to talk to you about my project, Implementation of Reinforcement Learning-Based Path Planning for Autonomous Vehicles. The focus of this research was on the creation of simulated vehicle models that could be used to implement reinforcement learning for path planning purposes. To begin, path planning is the process of computing a path for a robot to get from point A to point B. This can be done in many ways, of which I will show two over the course of this presentation. The problem with path planning, however, is that we often find ourselves operating in unknown environments. So we need to design path planning solutions that don't require us to know everything about the environment the vehicle operates in and how it responds to the way our vehicle interacts with it ahead of time, but rather the algorithm must learn over time the best actions to take, given previous outcomes and given our goals. This is what reinforcement learning achieves and why it is so important. So now for the first phase of my research. In phase 1, I learned Robot Operating System, or ROS, which is a software framework for robot development. I then needed to be able to use ROS to implement simple path planning algorithms with simulated vehicles. So in this phase of the project, I learned how to use Linux, I learned how to write ROS code, from simple ROS nodes to much more complicated and powerful ROS code. Once I felt truly comfortable coding with ROS and commanding robots, as well as extracting and manipulating sensory data from them, I began to implement a path planning algorithm known as randomly exploring random tree. The RRT algorithm takes in a map of the environment ahead of time and plots the path. Notice how this is very different from reinforcement learning, which uses online adaptive algorithms that learn in real time. The RRT algorithm then places little dots all over the map and finds a way to connect them in such a way that it avoids walls and all other obstacles until it reaches its goal location. So this is certainly not an optimal path, as we will see in the video demonstration at the end of the presentation. I achieved this implementation by having one computer work out the algorithm and the commands, and another one running the simulation and having them communicate with one another. In phase 2, I learned to create my own unique vehicle models that could allow me to implement reinforcement learning later on. I also began exploring more advanced functionality available through ROS. In phase 2, I learned SDF code, which is an XML code format that is used to create robot simulations. This is used to define the robot's physical shape, as well as their weight and other physics parameters that are important to define for the simulator's physics engine, as well as any attachments like cameras, laser sensors, and localization sensors. I use these models to implement P, PI, and PID controllers, which I was learning at the time in my controls course in order to test them. In this phase of the project, I also began to learn about more advanced tools available through ROS, including computer perception tools like OpenCV, which allowed me to write a program in which my robot moves itself around a yellow, circular-ish path by first identifying the color yellow and making its goal to keep moving forward as it follows a red dot, which is programmed to remain a constant distance away from my robot, always remaining centered around that yellow line. Lastly, and most exciting, comes phase 3. In this phase, I began to learn about control systems, as well as reinforcement learning and the amazing research developed here at UTA in this field by my co-advisors, Dr. Lewis and Dr. Wan. The ultimate goal being to implement a reinforcement learning algorithm to achieve path planning with my vehicle models. Most importantly, I was able to successfully implement reinforcement learning algorithms developed here at UTA by using the algorithm to plan a path in real time to drive my vehicle 10 meters in the simulation in one dimension, as well as a more complicated version that drives my holonomic vehicle in 2 dimensions simultaneously, bringing it from 5 meters in the x direction and 10 meters in the y direction back to the origin of the simulated environment. All of this I will show in the video demonstration at the end of the presentation. In conclusion, through this project, I was able to learn how to use Robot Operating System. I learned about path planning and various path planning algorithms, various machine perception tools like OpenCV. I began my education in control systems, and I began my journey into reinforcement learning. The next step for me will be to continue to learn reinforcement learning and other machine learning approaches to reach a proficiency level that will allow me to one day contribute original research of my own to this exciting field. My next implementation will be a more robust reinforcement learning algorithm that seeks a minimum time energy optimal policy solution. Most importantly, I would like to acknowledge and give thanks to my co-advisors, Dr. Frank Lewis and Dr. Yan Wan, as well as the College of Engineering Research Experiences for Undergraduates program, and Dr. David Wetz, the College of Engineering Director of Strategic Initiatives, for their work that aided and funded this opportunity for me to learn beyond the classroom and discover areas of research that I hope to continue working in and contributing to for years to come, and as I progress to my graduate education in the near future. I would also like to give thanks to other members of Dr. Wan's DNNC laboratory, my colleagues, Bishu Tsubedi, Wushuang Liu, and Peiliang An, for lending me their time and help during this project, and Lu Zhao for her work developing algorithms that simulate reinforcement learning in MATLAB, as well as Cody Lundberg from the UTA Research Institute. I would also like to give thanks to the National Science Foundation for the grant funding that partially funded my position at the DNNC laboratory. And of course, I would like to thank the UTA College of Engineering for hosting the Innovation Day Fair, giving me the opportunity to showcase the research I've been fortunate enough to conduct here at UTA. This final demonstration is going to come a little fast due to time constraints, but here you see the RRT path to my goal location being developed and plotted in MATLAB. And now you see my robot actually following this predetermined, very non-optimal path. After this, we will see my robot tracking a yellow line by following a simulated red dot that was programmed to remain at a constant distance away from my robot and always remaining at the center of this yellow path. And lastly, after this, I will demonstrate the reinforcement learning path planning, first in one dimension and then in two dimensions. First will come a portion of the MATLAB program that is responsible for the policy that is followed by the simulated vehicle that I programmed to be the actor which applies the policies and yields environmental responses for the system to learn from. Notice how quickly the robot approaches the origin before slowing down at the perfect moment. Once again, my name is Evans Morales, and thank you for listening to my presentation.